This video covers division of radical expressions. It's a continuation of the previous video where we multiplied, added, and subtracted. So for this video, there are essentially two types of problems. The first type of problem represents example 1 and example 2 represent the first type of problem. And example 3 to the end of the problems represent the second type. You want to notice the difference between these two problems, the two types. So the difference is in the denominator. This denominator has two terms, and the rest of the problems here, starting from number 3, have only one term in the denominator. We will use the conjugate that we learned in the previous example to complete example 1 and 2. And then for example 3, we don't have to use conjugates. Let's take a look at the directions. We want to basically divide, simplify, and then rationalize the denominator. So this part might be new. Anytime it says to rationalize the denominator, it means to write your final answer so that you don't have a square root or a cube root or any radical in the denominator. Your final answer should have no radical in the denominator. The way to eliminate the radical for the first two examples is to multiply by the conjugate of the denominator. And it's just going to be the same thing that you have here, but opposite sign. Remember from the previous video, when you multiply conjugates together, your answer will have no radical. And also you want to notice that you have to multiply the numerator and the denominator by the same quantity. If we look at this fraction carefully, this fraction is equivalent to 1. 1 times anything will be the same quantity. So when you multiply by 1, we don't change the problem. That's why this is okay to do. You can multiply by any form of 1 for these problems, and that's the whole idea. So let's see. We're going to use the distributive property in the numerator. In the denominator, you have to FOIL. Just like in the previous video, the like terms here will give us 0, so those will always go away when we multiply by conjugate, and the first and the last are perfect squares. Hence, we do not have a radical in the denominator anymore. Square root of 4, that's 2. Square root of 9, that's 3. 2 minus 3 is -1. So no radical. I can make this look just a little bit nicer where I just take -1 and I can distribute it to the numerator. So we could do that. It just makes it look cleaner. And this is the final answer. Second example, same type of problem. We have a binomial in the denominator. So the idea is multiply by 1. Which in this case, 1 is going to be square root of 6 plus 3, right? The conjugate, just opposite sign. So it looks like that. However, a little bit different than the first problem, I have to FOIL in the numerator. Why do you have to FOIL? Because we have two terms. Right here, we just had one term, we just distributed. But we have to FOIL. So FOIL numerator and also FOIL the denominator. Let's see what we get. You can pause the video, by the way, and try to do the problem yourself and then go back and check your work. All right, so if you notice again in the denominator, your like radicals give us 0. Square root of 36, that's just going to be 6 minus 9. So that's going to give us -3 in the denominator. In the numerator, let's see, 6 minus 6 is 0. So this is 0. And then I have 2 square root of 6 minus 3 square root of 6. That's just going to give us negative square root of 6. And I could simplify the signs and just write my answer in that form. This is my final answer. Be careful, a common mistake is to reduce 3 and 6. You actually cannot do that. The reason being is that 3 is not inside the square root. If you're going to reduce for your fraction, then the numbers should be in the same place. They're either both inside the square root or they're both on the outside. In this case, like I said, they're not in the same place, so we cannot reduce them. That's the final answer. Second type of problem starts with number 3, where we just have one term in the denominator. There are a couple ways to start the problem. There is no right and wrong on how you could start the problem. One way is to take a look at your problem and see if you can reduce the fraction, or see if you could take the square root or simplify any of the square roots. And the second way would be just to directly eliminate the square root and then simplify second. So it depends on whichever way you think is easier. I'm going to start this problem off by reducing the fraction and also telling you that since these are both square roots, I could just write this problem as one large square root. I could just write it this way. So you could interchange between the two. It's up to you whichever way you want to write it. You could leave it as 2 separate square roots or write it as 1 square root. But I can reduce, so what I'm going to do is reduce first. And when I reduce here by 2, I just get square root of 7 over square root of 3. And so now it's completely reduced, and I have to ask myself, how can I get rid of square root of 3? Well, what you really need to do is just get a perfect square in the denominator. Perfect square would be like 1, 4, 9, 16, 25. Those are perfect squares. 3 is not a perfect square. But I can remember that I can multiply by 1, any form of 1 that I want. So how do I make this into a perfect square? Well, what if I just multiply by root 3 over root 3, right? So that's 1, so it doesn't change the value. But 3 times 3, that's 9, and 9 is a perfect square. So then I can use that. So we're going to get square root of 21 over square root of 9. And once that happens, square root of 9 is 3. Square root of 21 we can't simplify, so we leave it like that. So I have rationalized the denominator and I have simplified the problem, and this is all we could do here. And so this is completely done. Let's take a look. I believe there are 3 more examples. All right, so these 3 are very similar to, hopefully you could see this, very similar to the example we just did. So for this problem, I noticed that I cannot reduce the problem, but I can take the square root in the numerator and in the denominator. We could simplify the square root. Square root of 4 is 2, so we can just write 2 square root of x. And square root of y squared, we know that y represents a positive number, so I can just write y square root of 3. Okay, so I just simplified the square roots. I end up with square root of 3 again, and we know that we have to get a perfect square, and we know that if I multiply by square root of 3 over square root of 3, that would change this, make it into a perfect square. It'll make it 9, which is what we want. So we have 2 square root of 3x and we have y times the square root of 9. The numerator is simplified. We can't do anything with it, so recopy. Denominator turns into 3y. And remember, you cannot reduce. This will be the final answer. Let's take a look at number 5. So this, along with number 6, these are cube roots. So we have to think about perfect cubes instead of perfect squares now. Right? So a perfect cube is not the same as a perfect square. Perfect cube. Remember, a perfect cube, 1 is a perfect cube, 8 is a perfect cube, 27 is a perfect cube. Those are all perfect cubes, right? So we have to think about perfect cubes. We have to get a perfect cube in the denominator. I noticed that I can actually reduce here. We could reduce by 5. So let's do that. Just makes the number smaller so it's easier to work with. I get cube root of 2 over cube root of 3. Okay, this is simplified. Now what am I going to multiply by? Like I said, 3 is not a perfect cube, but we did say that 27 is. So 3 times what is going to give me 27? 3 times 9. So we want to multiply by cube root of 9 over cube root of 9. So that's how we're going to get 27. So let's go ahead and write what we get. We cannot simplify cube root of 18, so that stays. Denominator becomes 3. And our problem is rationalized in the denominator. Last example, again, we have cube roots. This should be cube root of, cube root of x to the 5th. It's a little bit smeared for some reason. All right, so I said that instead of simplifying or reducing our problem, we could just go ahead and start multiplying at the very beginning. So I'm going to show you that you could do that. You could do it that way as well. So in this case, I can reduce, and I could also take the cube root of the numerator. But instead of doing that, let me just show you the other way. So I can just leave this problem the way it is, and I could think about what I'm going to multiply by. So I need to multiply by cube root of something. So you want to think about this. You want this denominator to be a perfect cube. 9 is not a perfect cube, but we know from the previous problem that 27 is a perfect cube. So 9 times what is going to be 27? It's going to be 3. We need to take into account that we have x, y. So we can't leave it as xy. I have to figure out what the perfect cube is. So x is not a perfect cube, neither is y. However, x to the 3rd is a perfect cube, y to the 3rd, right? Anything with an exponent of 3 is a perfect cube, which means since I already have one x and one y, I just need 2 more x's and 2 more y's. So multiply by x squared, y squared. Right? So that's going to make this 27, x to the 3rd, y to the 3rd. That is a perfect cube. Everything's a perfect cube. The number is a perfect cube, the x is a perfect cube, and y is a perfect cube. And that will eliminate the radical in the denominator. Let's multiply. Okay, so one little thing here. We would like to make sure our answer is simplified. if I take a look at the numerator, x to the 7th, we can divide the index 3 into our exponent 7. So I can actually simplify the cube root. You're going to get, so this is from before, but you should get x squared, and inside the radical will be 3xy squared. The denominator, 3xy. So I was able to simplify the cube root, and so we want to make sure we do that. And then the last thing I want to make sure is just see if I can reduce this, which I can. I can reduce one of these x's, and so this right here is my final answer. Okay, so that's our final answer, and that's completely, it's simplified, and the denominator is rationalized.